Hi, so today I'll be talking to you about revolutions and how to find volume using revolutions. So let's say you're given the graph y is equal to f of x, and you want to find the volume of the area from a to b of f of x when it's revolved about the x-axis. So what I like to do for these type of problems when I don't know what to do is draw the three-dimensional image. So this would be the three-dimensional image, and you can see that this volume would just be an infinite sum of circles. And we know how to find circles. That would just be area is equal to pi r squared. So to find the volume of this infinite sum of circles, we would take the integral from a to b of the area in respect to x. And we would do this in respect to x because we're revolving the area about the x-axis. If you are revolving your area about a line that is x equals something, then you would be integrating in terms of y. And if your line is y equals something, then you would be integrating in terms of x. And the x-axis is y equals 0, so we're integrating in terms of x. This is because if you look back at this graph, so you can see that the radius of the circle is f of x. And because this is in terms of x, we are integrating in terms of x. So going back to this expression, we can simplify this further to pi times the integral from a to b of f of x squared dx. And this is because the area is pi r squared. And because pi is constant, you can take it outside of the integral. And then your radius is just f of x. Because if you look back here, see this line is just f of x, and that is your radius of the circle. So you would use that as your radius and the f of x squared, and then integrating in terms of dx. So common mistakes for these type of problems is confusing revolutions with cross-sections. And they're very similar, but for revolutions you have the pi out front because your area would always be a circle, so it would be pi r squared, and you'd have your pi out front. But for cross-sections, a lot of the times your cross-sections would be semicircles or isosceles trapezoids, and that would have a different constant out front. Like semicircles would be pi over 8. So that's a very common mistake. And the next one would be forgetting to make your integral in terms of y if you're integrating in respect to y. So it's really easy to forget that your a to b, your interval would be different because you need to change it to whatever your new interval is in respect to y, and also changing the f of x to f of y, and also dy into your calculator. So for example, if you're given the equation x squared plus y squared equals 9, you would have to rewrite that to x equals plus or minus square root of 9 minus y squared. And then you'd be able to get rid of that plus or minus by determining the sign if it's in quadrant 1, 2, 3, or 4. And this is really easy to forget because we're used to doing things in terms of x, but you need to remember that it's not in terms of x, it's in terms of y, therefore you need to put your equation in terms of y. And the last common mistake is forgetting to take away the area of the inside part of a washer. So the volume equation for a washer would be outer radius squared minus inner radius squared. So it's really easy to forget that each part is squared. A lot of people do outer radius minus inner radius all squared, or just forgetting to take away the area of the inner radius in general. So yeah, definitely watch out for these common mistakes. So let's do an example. The problem asks you to determine the volume of the solid obtained by rotating the portion of the region bounded by y is equal to the cube root of x and y is equal to x over 4 that lies in the first quadrant about the y-axis. So this is a really good problem because it includes a lot of the common mistakes. It's revolved around the y-axis, and also there is a part that we need to take out in the washer. So first, since it's y-axis, you want to convert all your equations in terms of y. So y is equal to the cube root of x would go to x equals y cubed, and y is equal to x over 4 would go to x equals 4y. Then what I like to do is draw in my outer radius and my inner radius. So Sometimes it's hard to see what your outer radius and your inner radius is, but if you're picturing the 3D image in your mind, and the area of this is rotating around the y-axis, then you can see that this line would be your outer radius, and this line would be your inner radius. And you have to see what your outer radius function would be. So this line is y is equal to x over 4, or x equals 4y. So that would be your outer radius. So you could put 4y as your outer radius squared, and then your inner radius is this part, which is connecting to the y is equal to cube root of x, or x equals y cubed curve. And then you would use y cubed as your inner radius and square that. And you would find your intervals by finding the intersection point, and we can see here that it intersects at 0 at 2, at y equals 2. So you would be integrating from 0 to 2. And because you're integrating in terms of y, you have to have your intervals in terms of y as well. So this would be your final equation that you would put into your calculator, and usually the AP problems for revolutions are on the calculator section for the FRQs, so you don't really have to worry about doing the integration manually. You can just plug it into your calculator. And for our purposes, we're just going to set up the integrals. We're not actually going to solve for them. But a really neat way to save some time when you're taking the AP test is to store your functions into your calculator, and that will save a lot of time plugging in numbers into your calculator. So as you can see, what I did here was I stored x equals y cubed as f of y and x equals 4y as g of y. And if you put this into your calculator, you won't have to constantly write out y cubed and 4y. You can just use f of y and g of y, or y1 and y2, whatever's on your calculator. And I also stored my intervals from as 0 to 2 from a to b, and you can do that on your calculator. Just use the store button. And this is really helpful for the problems where they have you revolve it around the y-axis and the x-axis, and the line y equals 2 and the line y equals 1. So when you're doing a ton of problems, it's really annoying to have to manually put in every single number. So if you do this, you can save a lot of time. So for this example problem, we'll be determining the volume of the solid obtained by rotating the region bounded by y equals x squared minus 2x and y equals x about the line y equals 4. So because we're rotating the area around y equals 4, we know that we'll be integrating in terms of x, so we can have a dx there. And that's because y equals goes with dx and x equals goes with dy. That helpful little trick that I said on page 1. So next we want to determine our outer radius and our inner radius. So what I like to do is draw the graph. So I drew the graph with our two functions and also the line that we're rotating about, y equals 4. So we want to find what the outer radius would be by seeing which function is farther away from the line that we're rotating about, and that is y equals x squared minus 2x. So our outer radius wouldn't just be x squared minus 2x, because this is not our outer radius. We also have to take into account that our line that we're rotating about is y equals 4. So our outer radius would actually be 4 minus x squared minus 2x in parentheses. And our inner radius wouldn't just be x, it would be 4 minus x. Because if it were x, then this would be our radius. But because it's 4 minus x, we have 4, so 4 would be here, and then taking away this part, so it would be here, 4 minus x. So when we're setting up our integral, it'd be pi times the integral from 0 to 3 of 4 minus parentheses x squared minus 2x parentheses squared minus 4 minus x all in parentheses squared. And that's just our outer radius minus our inner radius. And there's our dx. And if we want to do that trick like we did before with making it simpler and easier to put in our calculator, we can set this equal to g of x and this equal to f of x. So then it would just be 4 minus g of x squared minus 4 minus f of x squared. And we can also set our intervals a and b as 0 and 3, and that would make it a lot easier to put into a calculator. Yeah, and that's basically as hard as it gets. A lot of the AP questions are just like this, and it doesn't really get much harder. And if you want extra practice, you can look at my worksheet. And also there are a ton of really great AP questions from past AP FRQs. Usually they're numbers 1 or 2 because they're on the calculator section. And you can find a lot of really good practice problems there. But these are probably the hardest that you'll see. Thanks for watching this video. I hope it helped you, and good luck with calculus.